Welcome back to Conceptual Physics at Delaware Tech, Chapter 23, Electric Circuits, Part 2. So we're actually going to talk about the circuits themselves now. Circuit is any path along which electrons can flow from the negative terminal to the positive terminal in a closed loop. So the loop has to be completely closed. It's the same as if you had a closed loop for a water pump shown down here in the bottom left. The pump provides the energy to pump the water through the line, and you might have a valve to stop it, but once you stop it, the flow stops. And the same thing happens when you have an electrical circuit on the right here. If you got a switch that opens up that circuit, it's no longer a closed loop and no current will flow through at all. You have to close the circuit, close the switch, and then now you have a complete loop for which the current can flow. That's a complete circuit that allows continuous flow of electrons, no openings, no gaps. Now, just a little important craziness. I hinted at this once before. Ben Franklin in 1748, he had determined that there are two kinds of charge, and he had to name them. So he named them positive and negative, but the question is which one is positive and which one do you call negative? So he named one positive and he named one negative, but he guessed that when current was flowing, electricity was flowing, he thought it was the positive charges that were the ones doing the moving, not the negative charges. You have to remember, this is long before the discovery of electrons by J.J. Thomson, and it was even longer before the discovery of protons. So the identities of these particles and what they were actually doing in a circuit was completely unknown to him at this time. He had to just assign one. So because of this, he thought the positive charges were the ones actually doing the circuit. So to this day, we make believe that it's the positive charges that are going around in the circuit, but the reality is the electrons are going around in the opposite direction, but we always make believe it's positive charges going around in the direction opposite we know is really happening. So whenever somebody says, what is the current doing, we talk about these theoretical positive charges that are going in the opposite direction that the real electrons are going the other way. So just keep that in mind if you were to actually study circuits in the future. We always treat it as if it's the positive charges moving. The math becomes exactly the same. You're just making believe that everything's going the opposite way. So circuits are generally connected in two basic ways, as well as combinations of these two ways. We have circuits that are quote unquote in series or series circuit, and this is a circuit that's essentially one big circular path. You might write it as a big rectangle, but it's one closed loop for the electrons to flow around. They'll start at the battery or the voltage source, and they'll flow around the wires and then come back to the voltage source again. If it's a single loop, we call that in series. And the reason why it's in series is if this loop has resistors on it or lamps on it or appliances on it, they're all lined up somewhere along the length of this single loop. So they're all in series. They're one after the other in the loop. So that's in series. And but the other way to create circuits is what we call in parallel or parallel circuits. And these are circuits that have branches. So you might have one circuit, but it branches off to a second circuit and might branch off to a third circuit. And I'll show you what these look like, so you're not just imagining what these things are. But you have a bunch of different circular paths that you only count the paths that will include the voltage source. So it would be a voltage source going around to one lamp or one resistor and then coming back to the voltage source. Or you have the voltage source going, and then instead of going to one lamp, you go to a different path that might go to a different lamp or a different resistor, and then come back to the voltage source. And you can have multiple ones. These all are parallel pathways for the current to flow. They flow in different pathways, different branches. So here's a typical series circuit, and this is how we would diagram it on the bottom, and this is what it would actually look like on the left. So here we have a battery. There's a switch, so it's open right now, but if we close the switch, we'd have a closed circuit, and the lights would come on. But as you can see, there's a single loop of wire, and it goes through several different lamps, several different resistors that are going to take some of that voltage. Each will take their own amount of voltage from the battery until it's all all gone, and then it'll come back to the battery, and the electrons will pick up more energy, more voltage, and go around again and provide more energy to each of the lamps. So the current that's flowing around will be constant. It's the same wire, so the current that's in one part will be the same as the current in every part, because think of it as a pipe with water. The amount of water going through one part of the pipe has to be exactly the same as the water going through another part of the pipe if it's all one loop. So because of that, you have this circuit, and we're gonna make believe the direction is from the positive to the negative, even though we know the electrons are going from the negative to the positive. So we have this current going around this circuit, and we have these various resistors in the circuit. And it turns out we can, if they're all in the same wire, the same branch, like this, in the same loop, we could theoretically treat them as if they're one big resistor. We could add up all the lamps' resistance together and just add them up mathematically, and that'll tell us what all of them are working together, because it's all one loop of wire, one circuit. So the total resistance is just the sum of the individual resistance in this series circuit. And the current, the total current of this circuit is the same anywhere along here. So since it's a single loop, the number of electrons moving in one place per second is the same as the number of electrons moving in another place per second. They all have the same coulombs per second, the same amps everywhere along this loop. So all of the currents are the same. All of the I values are the same. And if you want to know what the I value is, you would take the voltage of the battery, which you can just read right on the battery. It'll tell you what it is. Let's say it's a 12-volt battery. And let's say we added up all the resistances, and they added up to 6 ohms. Maybe we have three different lamps. They're all 2 ohm lamps. So 2 plus 2 plus 2 is 6 ohms. Well, that's our resistance. That's our total resistance, total R. And we have a total voltage. The only voltage is 12 volts. 12 divided by 6 would be 2 amps. And that would be the amperage, the amount of current going through every point along here, going through each of our resistors, each of our lamps, and going through any point in the current. And that's for a series circuit. And the voltage, you start with, say, 12 volts, and eventually it's all depleted by the time it comes back to the battery. Well, that means each lamp will be using up some of that energy along the way. But if you add up how much is used by the first lamp and the second lamp and the third lamp, and add each of those changes in voltage from each of the lamps, you're going to get the total voltage from the battery, which you already know. Okay. So each of those voltage drops, you could figure out what the voltage drops are for each lamp if you know what the resistance of each lamp is, and you already know what the current is determined by looking at the total voltage divided by the total resistance. So you already know the total current. If you know the total current and you know the resistance of any one, you can multiply the total current, which is the same everywhere, times each of the resistances. So that's I times R, current times each resistance, and you can get each voltage drop for each of the lamps. So the problem with a series circuit is if any part of this is damaged, there is no circuit anymore. There's no closed loop anymore. If one lamp breaks, the whole circuit's dead. And that's the disadvantage to a series circuit. Now, a parallel circuit, you have multiple branches. So if you look at this, you see on the left here, you see a battery, and it's leading a wire from both terminals of the battery, and then it branches into 3 branches that each go to their own lamp. There's a switch for each of them. We're not going to worry about the switches just yet. But each lamp has its own circuit. So you can have the battery, trace the battery's wire through the first lamp and then back to the battery, or you can trace from the battery to the second lamp and then back to the battery, or you can have the battery traced to the third lamp and back to the battery. But you never will trace from one lamp to another. They're all on separate circuits connected to the battery. We don't zigzag around through different lamp circuits. You make one loop. You look at one loop at a time. So you can either look at the smallest loop, the next smallest loop, or the biggest loop. Each one will have only one lamp on it and the battery. So you have essentially 3 parallel circuits that are all using the battery as part of their circuit. And that's represented on the right with 3 different resistances that are each in their own pathway. And you can think of it when it comes to that first branch down here, you can think of it as splitting into 3 parts. You can either go to the first lamp, the second lamp, or the third lamp, but then it's going to all come back to the battery in the end. And we represent the battery with this double parallel lines. I just labeled the bigger one with a positive and the smaller line with a negative. So our current, because of Ben Franklin, we label our current from positive to negative. So you have that loop, you have the bigger loop, and you have the biggest loop. But they all go through exactly one lamp and the battery. And that's a parallel circuit. So in this case, because the voltage is coming directly from the battery to one lamp, or it's coming directly from the battery to another lamp, or the voltage is coming directly from the battery to a third lamp without going through one lamp after the other, that means every lamp gets to see the full voltage from the battery. And as a result, the voltage that every lamp sees, every resistor sees, in other words, the voltage across every resistor is exactly the same voltage. It's the voltage from the battery. So the total voltage is the same as the voltage across each resistor or each lamp or each device in a parallel circuit. They all get their own source of energy from the battery directly. And the current will be equal to, the current is proportional, how much current goes to each one is going to be different. Because think of these red lines as the electrons flowing through, or in this case, the positive charges flowing through. When you get to a branch point, some of them have to go one way and some of them have to go another way. Well, how do you figure out who gets how much? Well, each resistor, depending on how big it is, will determine how much current gets through that resistor. So the current that goes through any branch is inversely proportional to the resistance. Remember, current is voltage divided by resistance, voltage over R, V over R. That means current I, if it's V over R, that means it's inversely proportional to R, because R is on the bottom. So the amount of current that goes through any one pathway is dependent on the voltage, dependent on the resistor for that pathway, but it's inversely proportional to it. So how do you figure this out? Well, one thing you realize is if you add up all the currents for each of those branches, those horizontal portions of the branches, they all should add up to the total current that reaches the battery or leaves from the battery. All right. So in this case, the current is not constant everywhere. It will change every time there's a branch point. So every time you get a branch point, some will go one way, some will go another. You get another branch point, some will go one way, some will go another. Current is the flow of electrons. And it's not, if you split the wires, some electrons will go one way, some will go another. So the current is no longer constant in a parallel circuit, but the voltage that goes across all the devices is the same across all of them. So another characteristic of parallel, as the number of parallel branches is increased, the overall resistance, the total resistance, as if it was one resistor, is decreased. And this may seem a little weird. So if I had 3 different resistors, so each pathway has a different resistance, 1 ohm, 2 ohm, 3 ohm. Well, it turns out the formula for figuring out what the whole resistance for the circuit is if they were all squeezed together into one circuit, into one loop, is equal to 1 divided by the sum of all the 1s divided by each of the resistors. In other words, the total resistance is the reciprocal of the sum of each resistance reciprocal, as written in this formula. So if you have 1, 2, and 3 ohms, if you wanted to figure out what they all act like together for that whole circuit, you would take 1 divided by 1 over 1 ohm plus 1 over 2 ohms plus 1 over 3 ohms. 1 over 1 ohm is 1. 1 over 2 ohms is a half, 0.5. 1 over 3 is 0.33. Well, if you add those together and then take 1 divided by that, you'll end up with about 0.55 ohms. You'll notice that this resistance of all 3 together in a parallel circuit is less than even the smallest actual resistance in any one of these pathways. So you're in a parallel circuit. The beauty of a parallel circuit is no matter what your resistors are, they will act together as if the whole thing has much less resistance than any one in the group. And you can think of this as analogous to if you were in a store and it was time to go to the checkout line, and if there was only one line, you'd have to wait with everybody going through. You're another electron getting through the line. But if you have multiple lines open, even if they all go different speeds or there are different difficulties to get through the line, it's still much better than having just one line. And having 3 lines is better than having even the fastest line for this, because you have choices of where to go. And as a result, in a parallel circuit, the combined resistance from multiple parallel lines is always, always, always less than any of the individual resistances. In fact, it works out if you have 2 of the same resistances, the overall resistance is half of what they were. So if one was 2 ohms and the other was 2 ohms in 2 different parallels, your overall resistance is actually 1 ohm, half of either one of them. All right, when 2 lamps in a circuit are connected in parallel, the total resistance is A, less than the resistance of either lamp, B, the same as the resistance of each lamp, C, more than the resistance of each lamp, D, none of the above. Well, I just finished telling you if you have 2 identical lamps, that's 2 identical resistances. The total resistance will actually be half of either one of the lamps. So it's less than the total. Resistors in parallel are like extra lines in a checkout counter. You have more pathways for the electrons to go through, so that means there's a lot less resistance for the electrons on average to get through, so that makes the flow easier. And in the case of, say, 2 10-ohm resistors, if they were both 10 ohms, if you do the math, it's 1 divided by 1 divided by 10 plus 1 divided by 10 ohms. That works out to 1 divided by 0.1 plus 0.1, which is 1 divided by 0.2. That equals 5 ohms. So 2 10-ohm resistors in parallel, as if would behave exactly as if you had one circuit that had a 5-ohm resistor. It made it easier than either one of the 2 pathways. So always remember that for parallels. For series, they add together. If I had 2 10-ohm resistors, you'd have to get through both, and that's like going through 20 ohms of resistance. But you put them in parallel, you give 2 different pathways, 2 different ways for the electrons to get through. You drastically reduce the resistance of parallel circuits. All right, consider a lamp powered by a battery. All right, so battery we know is direct current. It's always making the current go around in one direction. In this case, it's in series, it's a single loop, and you're charging up a single battery. Charge flows A, out of the battery and into the lamp. B, only from the negative terminal to the positive terminal. C, with a slight delay after closing the switch. D, through both battery and the lamp. Okay, I'll let you think about that for a second. It's through the battery and the lamp. Now, what do they mean by this? Okay, charge means the electrons. The electrons are your charged particles. Look at answer A. A says out of the battery and into the lamp. So the electrons are moving super slow through this. So the electrons that are in the lamp, that are actually making the lamp glow, are the electrons that were either right before in the wire, or actually mostly the electrons that are actually already in the lamp, because they're not moving very fast, less than a millimeter per second. So most of the electrons that are lighting up the light right away were already in the light, right? Only from the negative to the positive terminal. Remember, electrons flow from negative to positive terminal, but that's charge flows only from negative to positive, but it's also flowing inside the battery as well. It's just all part of the same circuit. That's a little misleading. C, with a slight delay after closing the switch. Well, technically that's correct, but the delay is so incredibly small because it's essentially moving around at the speed of light. The field is moving around at the speed of light, so all of the electrons are moving almost instantly. The second you close the switch, they're all moving. The ones in the lamp, the ones in the wires, the ones in the battery, they're all moving pretty much simultaneously. Okay, so charges are the electrons that are already in all parts of the whole circuit, and that's the electrons that are throughout it. The battery is simply providing the voltage, the force, the driving force that moves them. It's the driving force that creates the electric field that appears instantly when you close the switch. As much as the charge flows within the battery, it also flows, whatever's flowing into the battery is also flowing out of the battery. It's just a constant flow. So charge flows through the entire circuit, and all of the charges are all flowing at the same time around this circuit. And just note that the charge flows towards the positive terminal, but the current flows to the negative terminal, and that's because Ben Franklin thought it was positive charges flowing. So this whole thing can be a little misleading. I wouldn't give you a question this ambiguous on a test. All right, so I've given you 3 examples of circuits with a lot of detailed calculations. I will never expect you to do all these detailed calculations, but there are bits and pieces of this you should be able to do. One thing you should be able to do is look at a circuit and tell me if it's a series circuit or a parallel circuit. This is clearly a series circuit, a single loop. And if it has 3 resistors, you should be able to tell me what the total resistance is. You just add them up. So in this battery, we have a positive and negative terminal. It's a 12-volt battery. So the current will go in the direction that positive charges will go. Of course, the electrons are going in the exact opposite direction. All right. If you were to look at the 3 resistors, since they're in series, they would behave as if it was a single resistor that had the sum of those charges. So the total resistance is the sum. That's what the capital letter sigma is. It's the mathematical symbol for sum of all the individual resistances. 1 plus 2 plus 3 equals 6 ohms. And if you know that it's 6 ohms and you know the battery's 12 volts, well, 12 volts divided by 6 ohms, remember voltage divided by resistance is current, and you can figure out that it has 2 amps of current. And that's the most that I would expect from you on this, and I would give you one piece at a time. Now, if you wanted to look at the individuals, because this is a series circuit, you should know that the current is exactly the same all the way through. The same number of electrons have to keep on pushing through the wire everywhere in the wire. And if you know the current, I, everywhere is 2 amps, and you know each of the resistances are 1, 2, and 3 ohms, you can figure out the voltage drop for each of these resistors. The first one is 2 amps times 1 ohm, or 2 volts. The second one is 2 amps times 2 ohms, or 4 volts. And the third drop in voltage would be 2 amps times 3 ohms, or 6 volts. Notice if you add up these 3 voltage drops, 2 volts plus 4 volts plus 6 volts, you get the 12 that we started with the battery. And that's why if you look in the black numbers here, you see we start with 12 volts before it hits the first resistor. It loses some of the voltage, those 2 volts across that first resistor, to become 10 volts. The second resistor takes away 4 volts, so we drop down to 6. And the third resistor takes away the 6 volts, and that leaves us with 0. And it's 0 until it gets back to the battery where it's recharged to 12 again. And that's what's going on here. Now, we also know that power is equal to current times voltage. So we just multiply current times voltage. We know the current for each one is 2 amps. It's always 2 amps. We know the voltage at each one is different. The first one is 2 volts. The second one is 4 volts. And the third one is 6 volts. 2 times 2 is 2 watts. 2 times 4 is 8 watts. And 2 times 6 is 12 watts. If we add these up, 2 plus 8 plus 12 is 22 watts of power that we need to make all 3 resistors work in this circuit if there were lamps to light up all 3 lamps. So that's how we would calculate the power for the whole thing. But you don't have to do all that. We also know that we have a 12-volt battery and 2 amps of current. 12 times 2 is 24. That's direct. You can either add up the individuals, but that's a lot more calculation, or just do the overall voltage of 12 volts and the overall amperage current of 2 amps. 2 times 12 is 24 watts. And that would be the analysis of a parallel. I don't expect all that. I give you one piece at a time, and you'd answer a question like that. A parallel, every lamp or every resistor has its own circuit. So we'd have a circuit that goes through one, circuit goes through the second one, circuit goes through the third, but there's no circuit that goes through 2 resistors. It's only 1 resistor and then back to the battery. We start with 12 volts. And that 12 volts gets to go through all of the resistors because you're splitting the wires. The current splits up, but the voltage from the battery, it's only coming from the battery. So whatever reaches each resistor is always the full 12 volts. There's nothing sucking away voltage before it gets to a lamp. The lamps are always the only lamp on that circuit. There are three versions of the circuit here shown in red. So each lamp gets the full 12 volts. So in a parallel circuit, all the resistors get the same voltage, whereas in a series that we just saw, it keeps getting depleted along the way. So in this one, we know the voltage that goes through each one, and we know the resistance of each one. We can figure out how many amps go through each one because we have voltage and we have resistance. Voltage divided by resistance is our current, and we could calculate each of the currents that go through each of the three resistors. 12 divided by 1 ohm, 12 divided by 2 ohms, 12 divided by 3 ohms gives us our three different amperages. Now, this is what goes through each one, so if you trace back, that means you must have started with the sum of this amount of amps, because this is how many electrons in terms of coulombs of electrons per second went through. So it must have been the sum that we started with, or 20. We must have started with 22 amps to have all these amps going through each resistor or each lamp. If you want to trace the amperage in red here, you can see that at some point you're starting with 22. When you hit the first branch, you know that 4 of them go to that bottom lamp. You know that 6 of them go to the next lamp, so now we're down to 18 because we removed 4 from the first one. We removed 6 from the second one, and that leaves the 12 amps to go through the third lamp. So they all have different currents this time, but the same voltage across each lamp or each resistor. At the end of going through the resistor, the current stays whatever it was through that device, but the voltage is down to 0. It uses all of the voltage for each lamp. That's different than before. Before you were depleting a little bit for each one because they're all in a row. Now each lamp gets all of the resistance because it's the only lamp or only resistor on each circuit. And that will leave, if you add back the amps that come back together when the branches come together, the 12 at the top plus 6 in the one below it, that'll leave you with 18 down that path. You add the 4 that came from the first one to the 18, and you'll end up regenerating the 22 amps of electrons, coulombs of electrons per second that flow back to the battery. So you end up with your 22. You could also do this by treating all 3 resistors as one resistor, using the formula 1 over R1 plus R1 over R2 plus 1 over R3. You add them up, and it's 1 over all of that. And that would give you that they'd all behave together as if it was one circuit with 0.55 ohms of resistance. Well, you know the battery is 12 volts. You know the resistance. If you divide 12 volts by this number, 0.55 ohms, you'll end up calculating the same 22 amps that you already calculated anyway. So there are multiple ways to get to this, depending on what information you're getting. Don't be overwhelmed by all this. I will never give you something this complicated. I'll give you one piece where I'll say, here's a voltage, here's a current, what's the resistance? Here's a current, here's a voltage, what's the power, or what's the resistance? I'll give you 2 things and ask you to calculate a third. I will not make you go through a whole circuit. I might give you a whole circuit and say, hey, there's the resistors. It's either in parallel or in series. How would they act together? So you would do this reciprocal formula for parallel resistors, or you would just add them up for series resistors. That's the most math I'm going to have you do on this. If you want the power, again, you take the current and the voltage at each one, multiply them together, and you see that each one uses a different amount of power, 48 watts, 72 watts, 144. You still have to add them up, but if you added them up, you would get the same number if you just took the total power of the total volts, 12 volts, and the total amperage, 22 amps, multiply them together, you'll still get the same total of 264 watts. So again, multiple ways to calculate anything. Just be aware of how to calculate things, but I'll never give you a complicated circuit. And this is a mixture of the two. I certainly won't give you this I put this in here in case you're interested. You can walk through and see it yourself. The top one has a series part, but the whole thing is a parallel circuit, so it's a mix. And I'm not going to go through this now. You can walk through this step at a time with PowerPoint and just hit the forward button, and it'll go one step at a time and show you how each thing is calculated. But this is more for advanced knowledge. I would never test you on something this detailed. Okay. All right. So let's go back to the regular part of the lecture. Parallel circuits are frequently how people wire houses. You have different devices coming out, and of course the circuit is because it goes to the device and then back to the wall through the same power cord. Your power cord has two wires in it. It goes to the device and then back to the wall. That's your circuit, and you have a lot of these along the wall. So the devices are linked up with each of them in their own circuit. So it's linked up in parallel. Just trust me that that's the organization. I won't test you in any detail on that. So as you add more and more devices to it, there's going to be more and more current that's necessary, because remember, each parallel branch requires its own current to flow through. And so if you add more and more devices, more and more current has to flow through. Well, if you have too much current flowing through, your wires will start to overheat, especially the main wire that's going to all the other wires. That requires a lot of amperage that's split up into all the pieces for each appliance. And if you have too many, you can get overheating, and that will cause the wires to actually melt and ignite and cause a fire in the house. And people have lost homes because they've plugged in too many devices into the outlet. They put some kind of power strip on there, and they've attached power strips to power strips, and they have adapters that split it, and they end up having 12 things attached to the same outlet in the house, and it just can't handle all those currents being drawn by different devices, and eventually you'll end up with a fire. Well, one way around that is to have some kind of bypass on it that essentially prevents your appliance, like a toaster or heater or a lamp, from even getting electricity. The wire just directs the electrons around it. The electrons would rather go through a wire that has no resistance than through a toaster that has a big resistance. So these bypasses are called short circuits. But parallel circuits, you definitely have this risk of fire. So in addition to the excess devices causing all this extra amount of current flowing through that can cause heating, you have to have other ways to prevent dangerous situations. So you don't want fires in the house, so you have to have something to protect you. And there are two basic ways that circuits are protected from overheating from too much current. The first one are safety fuses. And these used to be used in houses all the time. These have been replaced with circuit breakers, which I'll mention in a second. But we still use fuses in a lot of smaller devices. We might use them in power strips. We certainly still use them in cars. And what safety fuses are is it allows the current to go through them, and the current is in series. So wherever something is going through a device, you also have it going through this fuse. And the fuse has a thin wire in it that if there's too much current, the wire will simply melt and shut off that circuit. The circuit will just die because the wire melted inside the fuse. Then you have to unscrew the fuse and replace it with a brand new fuse in case this happens again. And you have fuses that just plug in, like the bottom ones. These are what look like in the fuses in cars. The top one is what the old fuse boxes used to look like in the houses. You'd have these little screwable fuses that you'd screw in. They're almost like light bulbs, but it's just a single wire in there that will melt if too much current goes through it. But these have been really replaced by circuit breakers in most modern buildings. Circuit breaker might look like a big box with a bunch of switches like this. And what happens is if too much current is going through these, the switches just flip themselves, and you don't have to worry about it. The power will go off, and then when that happens, first thing you do is you unplug whatever made the circuit breaker flip. You unplug it, you walk downstairs to the basement or go to the closet where this box is at. If you're in an apartment, these tend to be right in the wall somewhere. There's some box in the wall, and you open up a little door and you'll see all these switches, one for each of the rooms or one for each of the outlets. Hopefully they're labeled. and you'll see one has flipped over. All the others are in the original position. Well, you unplug whatever made it flip, and then you flip it back, and it's ready to go again. And then you just turn on what you're going to turn on. You're just careful about not plugging in your hair dryer and your electric heater and your electric fan and a second heater and your microwave all at the same time. I'm in an old house, and in the kitchen, I can't turn on the space heater and the microwave at the same time. The circuit breaker will go, and I have to go down 2 flights of stairs and flick this switch. This is actually my box. This box is going to be replaced soon, but the house is extremely old, but we're lucky to have circuit breakers instead of fuses in here, so it's a very easy fix. But that's what's used today to protect your circuits from overheating with too much current going through. And with this, we'll stop here.